Hello, everyone. Welcome to the session of developing MIPI solution with FPGAs. My name is Masashi Taiyama. I'm a principal application engineer at Lattice Silicon Valley. Today, I'd like to talk about Lattice MIPI solution using our FPGAs, IPs, and different designs. This is the agenda. First, I'd like to briefly explain about MIPI CSI-2 standard. Then, I will introduce Lattice FPGA devices targeting for MIPI solutions, as well as MIPI and video-dedicated IPs and different designs we offer for customer designs. Lastly, I will pick up one of our MIPI different designs and talk about its design architecture and design flow, including IP generation and timing constraints, followed by functional simulation and tips about hardware debug. Now, let me explain about MIPI CSI-2. MIPI stands for Mobile Industry Processor Interface. They made two major standards for video applications. One is CSI, and the other is DSI. CSI stands for Camera Serial Interface, mainly focusing on image sensor interface. It has a dedicated clock lane and 1 to 4 data lanes. Both clock and data lanes use sub-LVDS for high-speed data transmission using DDR. Data lanes go into low power mode with 1.2 volt single end in every horizontal and vertical blanking period. Clock lane has two options. It can stay in high-speed mode during the whole streaming period, and that is called continuous clock mode. On the other hand, it is allowed to go into low power mode during blanking period like data lanes. That is called non-continuous clock mode. ISQC is employed as sensor configuration interface. DSI stands for display serial interface, mainly used for display interface. It uses same PHY as CSI, but protocol is slightly different from CSI. Today, I'd like to talk about CSI-2. Lattice FPGA and IP support CSI-2 standard version 1.2. This figure shows layer structure of CSI-2 and DSI. Left side is a transmitter, and the right side is a receiver. You can think of an image sensor as a transmitter and FPGA as a receiver, for example. MIPI uses byte data as a basis unit to process the image data, so captured image data is reformatted from pixel data to byte data with clock domain conversion. After that, data is packetized and serialized in the file layer and sent through sub-LVDS connection to the receiver side. The reverse operation is performed on the receiver side to retrieve the original pixel data. Lattice offers corresponding IPs like pixel to byte, byte to pixel, and also IPs for the transmitter and the receiver. Here, I'd like to explain about low power to high speed mode transition of data lane. During the low power mode, both P and N signals are high at 1.2 volt, single-ended. That is called LP11. To begin the mode transition, P signal goes to ground level first, while N signal stays at 1.2 volt. This is called LP01. After a certain period, N signal goes to low. This is called LP00. After LP00, the transmitter changes the mode from single end to differential and start high-speed data transmission. All transition timings are defined by MIPI spec. At the end of high-speed transmission, it goes back to LP11 with single-end mode. Here, I only show the mode transition of the data lane, but clock lane can also change the mode between low power mode and high speed mode in a similar way. Here, I'd like to explain about data packet transmission of CSI-2. When video data is not present during the blanking period, data lanes are in low power mode, indicated as LPS. It takes a predefined step to move from low power mode to high speed mode, as described in the previous slide. Then send startup transmission data before transmitting long packet data. Long packet data consists of packet header data and packet footer. End of transmission data is appended before going back to low power mode. Repeat this process until the end of the active video line. Short packet is usually used to indicate the boundary of the frame data, like end of frame and the beginning of the frame. This is the structure of short packet. It consists of 4-byte data. The first byte includes data type information, like frame start or frame end. And the last byte is error correction code. It can correct 1-bit errors and detect 2-bit errors. In case of 4-lane configuration, 1 byte is allocated to each data lane. Sync byte is the fixed data of hex B8, showing the beginning of high-speed data transmission. And trade byte indicates the end of high-speed transmission. These sync byte and trade byte exist on all data lanes. This is the structure of long packet. Packet header structure is similar to short packet. Now the middle 2 bytes indicate the byte count of data length of the payload data. Active video data appears here as the packet data. Data type information indicate what kind of image data we transmit, like row 8, row 10, and so on. 2-byte CLC data is appended after the payload data as a checksum. This is called packet footer. Sync byte and trade byte exist as same as short packet. As mentioned before, 1 byte is the unit to carry data in MIPI. When the bit width of pixel data is not a multiple of 8, we have to pay a special attention to convert pixel data to byte data format. This is a case of row 10 data transmission. Since 10-bit times 4 equals 8-bit times 5, 5 byte or 4 pixels is the unit to handle row 10 data. We take MSB 8-bit from every 4 pixel data and transmit first. Then, take LSB 2-bit from those 4 pixels and put together as the 5th byte and transmit. Repeat this step until the end of the line. Actually, this gives us the restriction with horizontal pixel count. In case of row 10, the horizontal pixel count must be always a multiple of 4. Otherwise, we cannot transmit all 10 bits of the image data properly. This is the way to send row 10 data, converting pixel domain to byte domain. Of course, we have a different way for other pixel formats. Now, I'd like to explain about relative FPGA devices to be used for MIPI solutions, as well as associated IPs and reference designs. Here, I show some FPGA lineups which support MIPI DeFi interface. CrossLink is our first-generation FPGA equipped with dedicated high-end MIPI DeFi IP, with up to 5 Gbps per lane as transmission speed. Soft DeFi is also available with up to 1.2 Gbps per lane. CrossLink Plus is a derivative version of CrossLink with built-in flash ROM to remove external device for its configuration to save power, space, and cost. CrossLink NX is our second-generation FPGA with hardened MIPI DeFi. Now the MIPI bandwidth is increased to up to 2.5 Gbps per lane with hardened DeFi and 1.5 Gbps with soft DeFi. We also have other FPGA families like Certus NX, Certus Pro NX, and others, but CrossLink and CrossLink NX are the only families with hardened MIPI DeFi. This table shows package lineup of CrossLink with DeFi capabilities. Except for 36-ball package, they are capable of 1.5 Gbps with hardened DeFi and 1.2 Gbps by soft DeFi. Up to 2 hardened DeFi IPs are available. Here, I show maximum number of channels with soft DeFi in case of 4-lane configuration, but more channels can be available if we use 1-lane or 2-lane configuration. This is a similar table for CrossLink NX. Hardened DeFi can achieve 2.5 Gbps per lane, and soft DeFi can achieve 1.5 or 1.25 Gbps per lane, depending on the package. This is a list of MIPI and video interface related IPs for CrossLink and CrossLink NX. CrossLink Design is supported by Diamond Design Tool, and CrossLink NX is supported by Radiant Design Tool. In case of CrossLink NX, we support end-to-end design by different designs rather than IP, which gives the customers more flexibilities. This is a list of MIPI-related reference designs. Most of reference designs uses multiple MIPI or video-related IP module and associated RTL modules. Some designs use only either MIPI RX or TX IP, and some use both IPs, like aggregation designs or duplicator design. Okay. Now, I'd like to pick one of the CrossLink refined designs, CSI-2, 4-to-1 image aggregation, and talk about that. This refined design controls same type of 4 CSI-2 image sensors and combines those images to one and output with parallel interface. 2 hardened RX DeFi and 2 soft RX DeFi were used to receive 4 CSI-2 streams. Output image can be either raw data or RGB data. This design was originally developed as a demo design, and you can check the image using our CrossLink NX VIP sensor input board kit with a HDMI display. The design can be easily changed to handle multiple use cases by changing parameters like number of MIPI data links, clock mode, and raw data depth from 8 bits to 12 bits. Regarding image data processing, we need to know the Bayer pattern to properly handle the image data, especially raw to RGB conversion. I will explain more about this later. The default parameter setting is Full HD or so-called 1080p with raw 10 pixel format using 4 lanes at 371.25 Mbps per lane. Clock mode is continuous, and parallel output data is RGB888. This is the block diagram of this different design with RGB output. 2 hardened RxD5 IP and 2 soft RxD5 IPs are used. Each sensor data is fed to RxD5 IP and then passed to byte-to-pixel IP module for clock domain conversion. After that, raw data is converted to RGB data. Then one of 4 image data is selected and sent out as RGB888 parallel data. Sensor configuration data is stored in the internal ROM and sent to the sensors. This different design is made for Sony IMX258 image sensor. This picture shows how 4 images are aggregated by this different design. The aggregation pattern changes by pressing the button switch on the evaluation board. Red images from the sensor on channel 0, yellow is channel 1, light blue is channel 2, and green is channel 3. All 4 sensor images are aggregated in default, then changed to the whole image of channel 1, channel 0, then channel 1, channel 2, channel 3, then vertical slice of 4 images, and back to the original quadrant image aggregation. Now, let's move to design implementation using Radiant tool. This is a screenshot of hardened IP configuration window. Hardened RxD5 is used on channel 0 and channel 1 in this design. You can change number of lanes, bandwidth, and other parameters for customization. Hardened D5 has a power down control pin for power reduction. Here, byte clock is a clock to handle MIPI data after the serial to parallel conversion is performed inside RxD5 IP. You can simply divide the bandwidth by 8 to get this byte clock frequency. This is the configuration of soft RxD5 IP. Soft RxD5 is used on channel 2 and channel 3. Soft D5 uses generic DDR primitives, and that's why it has some additional control and status signals. It is better to enable lane aligner when multiple data lanes are used. This will avoid data timing mismatch between data lanes. You can find RX54 setting in the bottom. This is very important in case that the byte clock generated from incoming MIPI clock and the internal byte clock are not in sync or speed is different. I will explain that in the next slide. Okay. Here, I'd like to explain 2 scenarios. The first case is that the internal byte clock is slower than the byte clock obtained from incoming MIPI clock. We can use RX54 inside of RxD5 IP to absorb the timing difference. If we have enough horizontal branching period between 2 video lines. Roughly speaking, if the branching period is 5% of the active video period, we can use close to 5% slower internal byte clock comparing to the one derived from MIPI clock, even though we need to reserve some margin. Let me check with this example. We can calculate the active data transmission time as 26.67 microseconds for 1080p Routine with 2 lanes at 360 Mbps lane bandwidth. Since the bandwidth is 360 Mbps, the incoming byte clock is 45 MHz as 360 divided by 8. So we can get the minimum byte clock speed at 45 times 26.67 divided by 26.67 plus 2, roughly equals to 41.86 MHz. You can use this number as a guideline to set the internal byte clock frequency. Of course, you need to put some margin. Now, let's think about FIFO depth. The amount of write data at the end of line is 1200 bytes per lane. On the other hand, the amount of read data is about 1116 bytes per lane when the FIFO write is completed. That means we need at least 84 bytes at FIFO depth. Considering some margin, 128 is a good number to use. Important thing is to know the length of the horizontal blanking period so that you'll be able to assess what the clock speed limitation is if you'd like to use slower byte clock. Also, you have to set the appropriate FIFO depth to avoid FIFO overflow, since read speed is slower than write speed. This is the case that the internal byte clock is faster than the incoming byte clock, using the same example. In this case, we know that we can finish reading the RX FIFO data before the next video data comes. But we have to avoid FIFO underflow, since read speed is faster than the write speed. Assuming to use 50 MHz as the internal byte clock against the incoming byte clock of 45 MHz. FIFO read time can be calculated by 26.67 times 45 divided by 50, which is about 24 microseconds. That means we have to begin the FIFO read at least 2.67 microseconds after FIFO write begins to avoid FIFO underflow. During this period, the amount of write data to the FIFO is 26.67 times 45. It's about 120. So the minimum FIFO depth is 120. We can pick 128 at the FIFO depth. Eventually, you need to make the FIFO depth deeper and wait time to start reading the FIFO longer when you increase the speed of the internal byte clock. Now, let me explain about another clock story. As mentioned before, MIPI handles video data in the unit of byte data. That means 32-bit data is transferred by every byte clock in case of foreign configuration. On the other hand, we'd like to handle video data in the unit of pixel data. That means we have to generate a new clock based on the pixel data rate. Let me show two examples. In case of row 10 with 2-lane configuration at 45 MHz byte clock, total bandwidth is 45 times 8 times 2 equals 720 Mbps. So pixel clock is 720 divided by 10 equals 72 MHz. In case of row 10 with 4-lane configuration at 46.40625 MHz byte clock, that is the setting of this reference design. Total bandwidth is 46.40625 times 8 times 4 equals 1485 Mbps. So the pixel clock is 1485 divided by 10 equals 148.5 MHz. Here, we can use byte-to-pixel IP for domain conversion, and that means we need to provide a pixel clock to this IP. We can calculate the required pixel clock speed by the calculation method mentioned here using pixel data type, number of lanes, and byte clock frequency. Ideally, we need to have the same data rate before and after this IP by providing a matching pixel clock. In case we cannot generate the exact clock speed to match the data rate, byte-to-pixel IP still works for data unit conversion if we can provide the faster clock. The required FIFO is automatically generated inside the IP, including FIFO write and read control. This is an IP configuration screen of byte-to-pixel IP. In this case, pixel clock gives the exact data rate on pixel clock side, but you can set higher value if this clock speed is not available in the design. Here, I'd like to talk about image sensor data format. Many RGB sensors use so-called Bayer format to transfer the video data. With this method, we get only one color component data among RG or B at one pixel location. As you can see, one line contains R and green alternately, and the next line contains green and blue alternately. Human eyes are more sensitive to green comparing to red and blue. That is the reason green data appear on every line. Now we need to create all RG and B pixel data on each pixel location. So we need to know which Bayer pattern your raw data begins with among these 4 patterns. This is the way to generate RG and B data on each pixel location. Let's assume we have to generate RG and B data at the pixel location indicated by the box using these 2 examples. In the first example, R data is already there, so we can just take the current pixel value for R. G data can be derived by taking the average of 4 pixels, top, bottom, left, and right pixel data. Similarly, B data can be derived by taking the average of 4 pixels, top left, top right, bottom left, and bottom right pixel data. In the second case, R data can be derived by 2 pixel average of left and right. B data can be derived by 2 pixel average of top and bottom. G data is already there, so no calculation is necessary. Since it requires 3-line data, we need to have 2-line buffer memory to execute average calculation. Okay, let's talk about timing constraint on Radiant 2. You can check the constraint by opening post-synthesis timing constraint editor. Here, I'd like to mention about 2 kinds of clock constraints: create clock and create generated clock. Create clock is used to define the original source of the clock, like external clock input or internal oscillator. Create generated clock defines the clocks derived from clock defined by create clock. Examples are PLL output clocks and clocks generated by the clock divider. This is an example to define MIPI clock come to the pins to soft RxD5. By selecting clock pin as the object type, we see many signals in the list. On channel 2 and 3, we can find MIPI clock I/O instance shown here. We can select these and set names like RX2 MIPI CLK and RX3 MIPI CLK. Now, let's find MIPI clock for hardened D5 on channel 0 and channel 1. This shows how to pick up the clocks for hardened RX D5. In case of hardened D5, it is difficult to find them by pin name. Please pick the signals with URW DCKHS as the clock source of byte clock. Now, we pick up two clocks for both hardened D5 and soft D5. Here, we need to be a little bit careful about naming and clock frequency setting. In this design, MIPI bandwidth is 371.25 MHz. That means MIPI clock frequency is 185.625 MHz, which is half of 371.25 MHz, since MIPI uses DDR. We can put names like RX2 MIPI CLK and RX3 MIPI CLK, and set 185.265 as the source clock frequency for the soft RX D5 as shown here. On the other hand, we didn't see the MIPI pin signal for hardened RX D5. Since hardened D5 timing is guaranteed by the device, we don't need to check its timing, and what we need is byte clocks coming out from the IP. As mentioned before, byte clock frequency is derived by dividing the bandwidth by 8. We can put names like RX0 CLK byte and RX1 CLK byte. Now, we move to Generated Clock tab. In this design, two clocks, CLK pixel and sync CLK, are generated by PLL, and two byte clocks, RX2 CLK byte HS and RX3 CLK byte HS, are generated by soft RX D5. Since all clock names are easy to understand, we can use these clock names listed here for under constraint. Now, we move to Clock Group tab. The main purpose of this constraint is to separate clocks comes from different clock sources. Since the design takes care of clock domain crossing signals, we can treat these clocks as asynchronous to avoid unnecessary timing analysis on false paths. MIPI clock and byte clock in soft RX D5 are in the same group, since RX2 CLK byte HS is derived from RX2 MIPI CLK, and same for channel 3. To avoid unnecessary timing violations, we need to set a false path and multi-cycle path. These constraints are already included in the sample project. You might have to enable or disable some of these settings according to your design. You can get most of the necessary information from IP user guide documents. So, please check the IP user guide documents when you make your design from scratch with these IPs. After completing the design constraints, we can run place and route to see whether the design meets the timing requirements. This example shows setup slack and hold slack with 4 place and route trials. We have positive slacks in both setup and hold. You can also check the timing analysis coverage by checking constraint coverage section. It's over 99.5% and well covered. Let's move to functional verification using a simulator. You can launch ModelSim from Radiant, then move to simulation directory and run the script on ModelSim prompt shown here. It begins compilation followed by the functional simulation. You will see a bunch of messages during the simulation. In the end, you should see the messages shown here to indicate all data are matched and simulation is successfully completed. This shows some sample message during the simulation. All output pixel data are compared with expected data one by one. Also, data enable and sync signal assertion and deassertion behaviors are reported. This shows a part of parameter files for data instances and simulation. To reduce the simulation time, 3 frames with 8 video lines are selected. Of course, you can change these values according to your needs. This is the simulation waveform showing signals between sensors and CrossLink NX. MIPI data are coming on all 4 lanes, all 4 channels in the same timing. In this simulation, I2C configuration continues while CrossLink NX receives MIPI data from the sensors. But this is only in simulation to save simulation time. On the actual hardware, video data from sensors begin after the completion of I2C configuration. This waveform includes output signals and data from CrossLink NX. There are no timing signals during vertical blanking period in case of CSI-2. Therefore, H-sync is generated based on the one video line period of the previous frame. That is the reason the first V-sync output from FPGA happened after the first frame is completed from the sensor. Video data output begins from the second frame after properly generating V-sync signal during the vertical blanking period. As described before, we need to do average calculation to generate RGB data from raw data. For that purpose, the video data output timing is delayed by 1 line, comparing to the input line timing. This is the close-up view of the one-frame transaction, including some internal signals. As mentioned in the previous slide, there's no timing signals during vertical blanking period, so H-sync and V-sync are generated based on the one video line period of the previous frame. This simulation shows both raw data and RGB data output. As described before, RGB data timing is delayed by 1 line. Now, I'd like to talk about hardware debug. When our FPGA is not working as expected, we should check some basic things first, like whether down equal high or not, since this signal indicates FPGA is properly configured or not. Also, we should check some basic signals like reset and clock before diving into the design itself. Okay. Then let's move to RxDefi check. There exist some key signals you can check as RxD5 output. HS-sync is an indicator to show high-speed MIPI data transmission. This must be asserted for every short and long packet transmission. SPEN is a short packet enable, so it must be asserted twice per every 1 frame period. LPAVEN is a flag to be asserted in the beginning of every active video line. Payload enable is video data enable. You can check the behavior of these signals and compare with simulation waveforms. Let's think about a scenario when HS-sync is not properly asserted. When HS-sync is not asserted at all, there are several checkpoints. First, make sure the sensor is properly controlled or not, like reset is released and clock is provided. Then we should check I2C configuration against the sensor. We can check whether ACK is coming back from the sensor or not. Also, you can check prop condition. Prop must be enabled by FPGAs I/O setting, or prop register must be populated on the board. Regarding RxD5 itself, you can enable extra debug signals and check data setup cycle. I will explain in the next slide. In RxD5 IP configuration window, you can enable simultaneous miscellaneous signal output so that you can check some internal status of the IP. Those include some internal state, termination control, and FIFO status. This shows some internal signal behavior of RxD5 IP when it detects short packet both for hardened RxD5 and soft RxD5. Before SPEN assertion, you can see LVHS state and term DEN value change, followed by HSDEN assertion. Even you don't know the meaning of each debug signal, you can compare the signal behavior with simulation waveform, and you can check whether it is working as expected or not. This waveform indicates the expected behavior of long packet transaction with brief explanation of each debug signal behavior. As similar to short packet enable check, you can use this waveform as reference to check long packet and related signal behavior. Another checkpoint is to change data setup cycle parameter of RxD5 IP. This value determines how long we wait to seek the start of transmission sync word while low power to high speed mode transition happens. Waiting too long could lead to missing sync word, and waiting too short could lead to false detection of the sync word. These are some key checking points when RxD5 is not generating expected output. This concludes my presentation. These are reference documents for today's presentation. You can get IP user guide and device datasheet from Lattice website. This is today's summary. First, I talked about MIPI CSI-2 specification, mainly based on protocol standpoint of view. Then, I introduced lattice FPGA devices, IPs, and different design for MIPI solution. Lastly, I picked up one CrossLink NX different design and talk about its architecture and design flow, including the debug section. I hope you enjoyed my presentation. Okay, now is the time for Q&A. Okay, the first one, is there MIPI CSI-1? If so, what is the difference from CSI-2? Okay, the CSI-1 is an old standard which defined only one data lane. At some later time, CSI-2 was introduced and it allowed 1 to 4 lane data lane configurations. And eventually CSI-2 is now popular, much popular. The second one, what are the pros and cons about continuous clock mode and non-continuous clock mode? Okay. In case of continuous clock mode, we don't need to generate so-called byte clock by ourselves, and that means we can simplify the internal design. On the other hand, since clock is continuously coming, it consumes more power comparing to non-continuous clock mode. In non-continuous clock mode, we have to generate a byte clock by ourselves, most likely using internal parallel. Also, we need to think about FIFO control in RxD5, so we need to be a bit more careful about our design. So it will be a power versus design kind of trade-off. Next question is, why do we have different D5 bandwidth among different device packages? Okay. Some low peak count devices have smaller number of power and ground pins. Also, QFN and wafer level chip scale package devices have lower signal integrity compared to BGA devices. So those are main reasons to limit the TX bandwidth. Next question is, what can we do when the timing doesn't meet after place and route? Okay. It depends on which path is causing a timing violation. Sometimes it can be resolved by adding more pipeline stages. If it is related to pixel clock domain, one option could be changing the number of pixel data output from byte to pixel IP. Default is 1 pixel data per clock, but you can change it to 2 pixels or 4 pixels per clock in some cases, so that you can reduce the pixel clock frequency by half or quarter, comparing to 1 pixel output. Okay, one more question. What is virtual channel aggregation reference design? Okay. MIPI allows to combine multiple video streams into one stream using logical channel IDs called the virtual channel. One example is the sensor bridge, which takes image data from 2 different CSI-2 sensors and output as a single CSI-2 stream. I didn't mention when I explained about CSI-2 short packet and long packet structure, but we can embed virtual channel ID information in each short packet and long packet header. On the receiver side, it checks this ID number in every packet to separate and extract desired CSI-2 stream. So virtual channel aggregation design uses multiple RxD5 IP and 1 TXD5 IP. Okay, this is the end of question. Thank you very much for your attention.